Yeah, we're going to continue our journey through the Alpine Himalayan belt and finish the story on the Aegean that we started yesterday. So we went through that. Convergence, slab retreat, tectonic accretion of Tethyon units, high pressure, low temperature metamorphism, recorded in rocks of the Aegean and the Cyclades. And then exhumation, back to the surface, in a context of slab retreat. So that's similar to what we've seen for the Western Alps and what Malika described in details this morning for the Somorari Nappe and the Eclogites. Burial exhumation. That's only part of the story. We saw with the Himalayan belt that there's then a high temperature overprint on top of this high pressure burial exhumation history. And the same is seen in the Aegean with these red crosses. Not these reds are plutons. These are granitic plutons. But these red crosses are places where you have migmatites at the surface, so high temperature, mid-pressure rocks. So we're going to move to that island, Naxos, which has preserved the best structural section going from high pressure to high temperature. So it's a good place to test how we go from one to the other, to characterize it. So this is Naxos. Very nice place to work, not too much vegetation, nice food, nice people. It's easy. You have some climb, but not so much, so it's a very nice place to work. So the island is about 40 by 20 kilometers in size and is dominated by schists and marbles. So this is the Mesozoic sequence, carbonate sequence of the margin of Eurasia and also the one of Gondwana that has been tectonically accreted in all the Alpine Himalayan belt, right? It's the same. And these marble and schists, they have preserved high pressure, low temperature metamorphism dated at 50 million years, not so far from the one of the Somorari, right? So the same timing. And it's preserved in the southern part of the island. But then these rocks have been overprinted by a mid-pressure, high-temperature metamorphism that grades from green schist facies in the south to amphibolite facies in the core of the island. And it's in the core of a migmatite dome that I'm going to describe in details. So you see these zones 1, 2, 3, 4. These have been mapped, and these lines actually. These are these isograds: biotite, chloritoride. So I should start with corundum, biotite, chloritoride, and then kyanite and sillimanite. So you have concentric isograds that have been mapped in this area. So you have marble and schist, their metamorphism, and they've been intruded by a granodiorite pluton dated at 11 million years. And that granodiorite pluton is probably if we refer to the subduction, it's probably the time at which the slab retreats in such a way that it's at 100 kilometers beneath that island at that time. And this intrudes the schists and marbles and crosscuts the isograds. So it's post-metamorphic, or part of the metamorphism. And then all of these rocks, plutonic metamorphic, are juxtaposed along low-grade units and even sediments in yellow, sediments that are conglomerate sediments, detrital, coarse detrital, along a tectonic structure, a marionite, which is very low angle. If you take it in the north-south direction, and that's the cross-section north-south, it's except for it's going around the dome like this. And it bears a lineation that is northeast, southwest, and kinematic criteria that tells you it's top to the north. But this detachment has a very strange shape, going from like this, goes around the island, and you find a little piece here on the other side. So at the same time, it's on the north-south section is not too much the dip is fairly shallow, but on east-west section, it's folded. So we call it corrugated. It's like that. Okay. So we're going to address the question, two questions: how we go from high pressure to high temperature, and what controls the dome formation. Dome formations, there are several models that have been invoked, either fold interferences with shortening direction that are perpendicular to each other, and that will lead to a map pattern like this, with shortening like this and shortening like that, either at the same time, so that's folding in 3D, or successively in time, like this and then like this. Another way to produce domes is by diapirism, gravitational instabilities. And the chance we have in Naxos is that everything has been proposed. So we can then address these different models and look at what were the evidences provided by the different researchers. The first that worked there, they mapped the isograds. That's Jensen, smart Dutch guys, that went into the Cyclades for geology. He did the geological map of Naxos, and he mapped the isograds, and he could show that the isograds are concentric and centered on the core of the dome, which he interpreted as being related to a dome up, and that might be related to diapirism. Another option was proposed just afterward by Gauthier, that the detachment might be playing a role, and it's then a 2D view of dome formation. Is really an antiform that should form in this sequence. And the idea being that beneath this detachment, the ductile crust would be exhumed and forming an antiform. It's not really a dome, that's an antiform. So it explains the antiform shape, but not really the dome in 3D. But it's in a way to connect the detachment with the structures that are underneath. So these guys proposed that there was two directions of shortening, concomitant with stretching in a northeast-southwest fashion, and that might explain the domes. So I'm not going to go too much into details of that, I think. Yeah, these are the evidences of folding that we find. We find the folds. Extensional, compressional, so that starts to be confusing. It's, okay, we have shear zones, normal folds, shortening, compression. So yeah, it's confusing. So let's go with how we address that question. So first we did the mapping, and we identified that actually this at first sight might look at monoclinal. It's marble schist. It's actually folded 3 times. F1, F2, F3. As we saw for the Lavario. And these are actually the folds that have been described. So maybe I should go through that. So there are isoclinal folds, but there are also upright folds. And here in that work, they've been taken at the same level. They say that upright folds are equivalent to isoclinal folds, overturned. That's not true. These type of folds, they form in a hot environment with the ductile rocks. These type of folds, these ones, the upright ones, they are mostly related to buckling, not to flexural sliding. So you don't want to mix folds like that with isoclinal folds like this. So again, by going back and forth from the scenery to the panorama to the outcrop, then you manage to identify F1 over printed by F2, and then upright folds at a large scale that are F3. So that's a schematic representation of that. And these folds that we see here in the scenery, you see that they are rotated by the dome. So what is the relative timing between folding and dome formation? The dome occurs before or after the folding? After. Huh? After. And the dome, see, it's consistent with also the folding of these detachments. So that's where there starts to be it's difficult to set up the relative timing. And what was the surprise in these rocks is to identify what we call second-order domes or subdomes. So within the main dome, there are other domes, and they are delineated by marble layers that show second-order domes within the first-order dome. I think I didn't put the things right in the order I was starting to think this morning, so I have my story a bit messed up. Okay, so that's here a section that has been done parallel to lineation, perpendicular to the detachment, in order to check from south to north what is the history of cooling and exhumation, making the assumption that cooling is related to exhumation, having material points going closer to the surface. And this has been done by biotite, white mica, and hornblende using argon-argon. So that's allowing to build the temperature time history. So I reached to that with the Western Alps, but I didn't tell you much of the details. We can do temperature time using hornblende is typically 500 degrees Celsius for argon-argon. So that's what we call the closure temperature, at the time at which the argon produced by potassium decay is trapped into the hornblende. And you need to find, in order to date with argon, you need to find minerals that contain potassium. And hornblende contains potassium. Biotite, muscovite, it's typically, muscovite is 350, and biotite, 300 degrees. So if you analyze the argon for hornblende, muscovite, biotite, you might build, get an age for each of these systems. If you're lucky enough to have in the same outcrop this diversity of rocks, then for a single point you can have the temperature time evolution. And this is what has been done here on several outcrops that were taken from a distance to the detachments that is almost outcropping to the north. So from 0 to 30 kilometers away. And you see that there is some kind of a trend, with hornblende being typically older than white mica, and white mica slightly older than biotite. So it makes sense. You have, for one point, in material point, you have systematically hornblende older than muscovite, older than biotite. And then looking on the north-south section, you see that the age are younging towards the north. So that's consistent with having exhumation earlier in the south and cooling earlier, as the detachment was active and exhuming rocks first in the south and then in the north. I think it's a very nice demonstration of that. Did you follow? So the story, keep in mind that it happens from 16 to 12 million years. That's about the time of the granodiorite emplacement. It's about the same age, and actually the granodiorite has recorded magmatic textures in its core, and then CS fabric on the edge that grade into cataclysite. So it's ductile to brittle. And that has the same logic of going from hot to cold as the rock is exhumed. So now we're going to go across that metamorphic gradient with different samples from here, this, which was called zone 3 by the isograd map of Jensen, and then we move towards the migmatite. And this was an important step. No, before that, it's no longer the case, I think. But let's say that the first approach in this type of environment was to take samples in different metamorphic zones and pretend they represent a single material point in space. But here we have an island which is 40 by 20 kilometers. Could we consider that as a one point, one material point? It's difficult, and we'll see that it's not the case. So then people would get PT from zone 3, PT from zone 4, PT from zone 6, and then build a single loop. Say, okay, that's the PT path for Naxos. Okay, the assumption is that this entire island behaved as a single block, rigid, in PT space. So what if we challenge that assumption, and when we take samples, different samples, and check the PT record? So that's the same, and I'm glad. So this program is very well organized. So Malika has shown exactly how she did it with the Somorari eclogites. So we did pretty much the same thing. We looked at the mineral assemblage, which was in contact with which. So here, garnet, fengite, plagioclase, in this rock of zone 3. So we can, thanks to experimental work that have calibrated these reactions in the lab, then we can say, okay, we have this mineral assemblage. That means that we are in this zone. And in this rock, there are metamorphic reactions that are shown by coronetic textures, coronas, with garnet going into muscovite, chloride going into garnet biotite, which documents two different mineral paragenesis. We call paragenesis the minerals that are in equilibrium, and documents here isothermal decompression. So let's see if you are on the good tracks. What does it mean in terms of tectonics? Isothermal decompression. What does the material point? Decompression. Exhumation. Subduction is the first step to bring that sample that was a sediment to high pressure. That's increased pressure. And then decompression, exhumation. And it's isothermal decompression. So this will reach to the next lecture, the last one on this Phanerozoic belt. It tells you that the temperature didn't change during exhumation. What do you think? Is it calling for fast or slow exhumation? If the temperature doesn't change. Okay, I'm not going to answer that. It's not, you're not there yet. That's fine. But we here see that it's isothermal decompression. Okay, let's move then now to the next exhumation. To the next sample, 4. Here we have staurolite, biotite, kyanite, which is consistent with this field. So it's not very well constrained, but this field in the PT path, which is slightly higher temperature than the previous one. So this point has been submitted, and it's at lower structural level compared to this foliation, and it has encountered higher temperature. And then it's been put back in contact with this one, so they have followed the same path of exhumation. So the fact that the sample 4, that is below 3, is higher temperature, what do you think? Does it logic? See, it's not really higher pressure. We don't really know, we don't have any insight on the pressure, except that it's within that range, but we don't see that decompression here. We can draw that line across it. Well, the idea might be, if it's deeper, it's higher temperature. That makes sense. At the time, and these are the minerals that are in equilibrium with that foliation. Huh? We're not talking about the F1 folds, it's the S2 foliation. Then zone 5 here, just at a lower structural level compared to 4, a slightly higher temperature. Well, we follow the same logic. The deeper we go, the higher temperature we have in the rocks. Okay, let's move now to zone 6. What do you expect in terms of temperature, pressure? Higher temperature. And so lower pressure, this is correct, this is what we found, but we were surprised at first. Why lower pressure? It should be, as we go down structural level, we should have higher pressure, right? So this, at first, it was not really intuitive, but we'll see. So that's 6, sillimanite instead of kyanite. Now you see the sillimanite here, in equilibrium with another type of garnet that is also constraining the PT, mostly the temperature for the garnet. So we have lower pressure for a sample that is coming from lower structural level. Okay, maybe the way out is that these rocks are migmatites. These didn't show any sign of partial melting. These are migmatites. So most part of this history recorded in these rocks is no longer preserved in these rocks because of melting. And really, I think what you record in these migmatites is the time at which they crystallize. It's not the prograde, it's the retrograde path. And if there are no minerals, there's no record. So it's the time at which these rocks crystallized. And what it tells us is that between the time at which this rock has recorded its peak pressure and the time at which these rocks have crystallized, there has been decompression. So there has been exhumation. And it's relative exhumation of these rocks compared to these ones. So there has been a motion of these rocks get closer to the surface compared to these rocks. So you see that's, you're starting now to play with different surfaces, material points, things that you can hold in your hand, and then surfaces that are immaterial, the surface topography. It's ever-changing, it's not material line. And isotherms, these are also lines that go across rocks. These are not material lines. So then, your brain starts to be a bit getting hot, because you have to play with material points moving relative to the Earth's surface, burial exhumation, and then isotherms moving relative to the material points. That starts to be tricky. And then you have time. And time I didn't put now. Okay, I forgot this story. Yeah, at first, these rocks, the migmatites, so this is our new map. These rocks, these migmatites, were considered as being a basement, very scant basement, compared to the Mesozoic platform sediments. And it's something that is very common in any type of maps. You know, maps usually, and stratigraphy has been done on sedimentary rocks, following the stratigraphy. So you go from Cenozoic, Mesozoic, Paleozoic, and that was the work of Werner that I mentioned in the first day. As long as you could find some way to identify the sediments, it was easy. And as soon as these guys got into gneisses, off, basement. Which is fair enough. You know, they are lying underneath, so basement. But the more we look at these rocks, the more we realize that they are younger than the sediments. In terms not of protolith, but in terms of metamorphism and processes, deformation, and so on. So, basement. And in this basement, what do we see? Blue. Blue is marble. Just from the map, you have something that is strange with this interpretation cover basement. What do you think? The blue is into the basement as big chunks. Is this consistent with the cover basement relationship? Not too much. Huh? So the people, they saw that. Huh? So they said, okay, maybe the cover has been infolded with the basement. And now we see a section like this, and we see cover that has been put into the basement. That's one way to do it. But okay, how to test that? Well, look for the contact between these marbles and the host rocks. And first, we looked at the contact between the migmatic gneiss and the paragneises or the schists that are in brown here. And what you see here is that, what do you think? You go from brown to white. The brown is biotite rich, layered, foliated rocks. Can you see the leucosomes here parallel to the foliation? So concordant leucosomes. And the more you go towards the left here, from where you are, the more quartz feldspar there is. And this is mapped as the basement cover transition. I think from what we see here, we can also propose that here there's a gradient of increasing leucosome, increasing granitic part, which might be interpreted as a gradient of partial melting. Still leaves us with a problem. Here it's more quartzo-feldspatic. If it was the same protolith, it's more quartzo-feldspatic than here, which is more iron-rich, iron magnesium-rich with the biotite. So where does the iron magnesium go? Well, first part of the answer is that we have lots of garnet in here that might incorporate these elements. And it's probably not the other way out, and that's an easy way out, which you cannot test in that outcrop, is that, well, the system, as soon as it went from metatexite to diatexite, which is what we see here, then became open. So we lose minerals by segregation, melt crystal segregation. I see your face. It's an easy way out. Huh? Say, okay, I've got a solution. I put the dirt down below the carpet. But we're going to see that it's not that stupid. So what does it look like inside the dome? Migmatites with different types of migmatites, metatexites with leucosomes concordant, diatexite with lots of enclaves into heterogeneous granite. And it's surrounded by leucogranite. It's highly deformed only on the southern edge. And if you look at the microstructures, it's not a pristine magmatic texture. You know, it's kind of grungy. If you look granite with a magmatic texture, you see uridral crystals, interstitial crystals. This look like more grungy. And probably my intent now is that part of these minerals are residual from the protolith, part are crystallized from the melt, and part might be peritectic minerals. Peritectic Peritectic, maybe not everybody knows that, huh? That term. The problem with the melting reaction, if you take, let's say, quartz, feldspar, biotite, aluminum silicate, for example, sillimanite, a typical reaction, it will go to melt plus garnet, for example. And the only part that was liquid is this. So you might have, if this reaction is partial melting, then you might preserve part of these residual minerals. And as a product of the reaction, you will have this peritectic mineral. Garnet could be, actually, feldspar could be one of these. K-feldspar, plagioclase could be. So it could be plagioclase, it could be K-feldspar. And when you're looking at this rock from the outcrop, you say, okay, this is mostly, or even better the previous one, this is mostly granite. But maybe it was not 100% crystallized from the melt. I might come back to that later if you ask. Okay, and then there's only slight hint of high temperature recrystallization that is shown by this undulatory extinction of quartz. That means that the quartz grain has been a bit like that, and its crystallographic orientation is a bit torqued. So that's why it shows undulatory extinction. And when you have a band of extinction like that at 90 degrees, or that are like this, making a sort of chessboard, that means that there are several gliding system, slip system that have been activated, and that's reproduced in experimental work and a test for deformation at solid state at around 600 degrees. So we know that has been a hit of solid state deformation, but not much. Okay, so yes, so at first sight it might seem difficult to measure that, but we tried it. Okay, it's not as precise than when you are in the sedimentary rocks with a nice bedding, but you can measure the general attitude of these, the general attitude of that foliation, the fold axis, the fold axial planes, the sort of the envelope of the folded layer. All these we measured, and this was the work of Seth Kuchenberg, and he measured all sorts of structures. And here, these two sets of lines. Okay, maybe I'll explain that too. The dark lines are measured from the field, and the red one is measured from on samples that have been collected in the field, and it's the magnetic structure, the magnetic foliation. In other words, it's provided by the orientation of magnetic minerals. So we wanted to compare both of these structures. It's not perfect, the match is not perfect, but at first order it works. So then we have measurements. And the idea then is to draw what we call the foliation trajectories. You draw the trajectories by extrapolating from your measurements, and so on. So if you're doing basic mapping, that's what you should start to do, is take a lot of measurements, as much as possible, and distribute them, and then you can start to draw the trajectories. So Seth did a wonderful job. He spent 1 month taking measurements on this area, which is about 10 by 20 kilometers. What went up and down, took about 600 samples for the magnetic foliation. And this is the map that came out of it. The first panorama showing the subdomes, it was by eye, just looking at this, I did like that. I thought, okay, I see it, but I want to demonstrate it. So this guy did the tedious work, and you can see one here, another one there, one there. Yeah, this shows with the magnetic, that's the magnetic fabric, and it shows also these rounded features. He did lots of cross sections. And then we came back to this early hypothesis. Are these reflecting polyfolding, diapirism, or another hypothesis that came into play is isostatic flow beneath the detachment as correlated with the activation of the detachment. Let's see. Because I think I've got the most schematic. Yeah, that's the most schematic view of it. Easier to see. We see drew here concentric lines to show the different patterns of the foliation. So what do you think? First, remember that we have in the mantle sequence here compared to the dome, we have fold F1, F2, F3. Do we find this fold pattern in these structures? Maybe here. Here you see that the contact between the pink and the brown is folded. So there is something to it. Do we see the effect of the detachment? Actually, maybe here. There is this strand here with the magnetic foliation that is diverging compared to that triple point. And that might be the effect of a localized deformation. But other than that, within the main or the first order dome, we see subdomes, at least 4 of them. Does it match the isostatic flow? In which case we should see 2 subdomes separated by a high strain shear zone. So we have a high strain shear zone in middle, but it would mean that there is 2 domes on each side of that shear zone. I think from my perspective, we see here more subdomes that are independent to each other, not only related to that high strain zone, and they share a similar envelope, which is the first order dome. So my interpretation is that we have something that is more looking like that, with a single envelope for all the subdomes that are contained, no cross-cutting relationship between the domes. So if you had polydiapirs, you'd expect one diapir, and then another one, and then another one. They should be cross-cutting each other. They seem to be sort of concentric. So I think this is a better way to represent it. Okay, so that was the structure into the dome. Now I just want to attract your attention on another tool that might be useful in that type of terrains. And Deepak should listen to that. I see that he's going. You should listen to that, unless you have to go. Dikes. So these are the marble and schist with a lot of dikes. Dikes everywhere. All the white stuff sticking out are dikes. And looking at them, well, we didn't pay attention to them at first, and then we thought, okay, maybe we can use them. So we start to measure dikes, and we realize that most of them, the dikes that are pristine plutonic magmatic fabric, they were either parallel or perpendicular to the lineation. So here it's a plane of the foliation, and the lineation is like this. So you have either dike perpendicular or parallel to the lineation. So this corresponds with what we call chocolate tablet structures. Chocolate tablet forms when you have one direction of shortening, and in the plane of flattening, you have 2 directions of extension, of stretching, sorry. And it results in chocolate tablet. The way I looked here 20 years ago. Don't laugh. I like these ones. These 2 dikes, they almost met. It's very romantic, but they never met. So these are the dikes on this side. So you see the foliation is like that, and the dike are cross-cutting this way. And this one is almost not transposed and has a magmatic fabric. On this other side here, you have the foliation like that, and the dikes are like this. So it's like that. So what it means or one way to interpret that is that this foliation had been already tilted before dike intrusion. Tilted towards the east in the east, towards the west in the west. What if we look now more carefully in these schists? They're actually full of dikes. Half of the rock is not schist, is dikes. But dikes that have been folded. So, at first sight, you don't see it. And once you start to look at it, then you find them. And you see the relationship between the folded dike, transposed dikes, and the ones that are magmatic. So what does it mean relative to these dikes? They intruded before rotation, before intrusion of this one. So then you start to build a story of deformation, magma intrusion, deformation, magma intrusion, and transposition. So we measured everything. And here, for example, we have a sheared dike, another folded dike. And that's for the east-west section. What happens in the north-south section? Well, the same. Dikes that are vertical with a magmatic fabric, but other dikes that are sheared. So it's not transposed here, transposed there. This dike is the same, so it corresponds to a single magmatic emplacement. So probably we have here a strain gradient, a shear gradient, or deformation, strain gradient I think is the best. And here this top, the schematic is consistent with top to the north, which is the main kinematic recorded throughout the island. And it's true on both sides, on the northern side and on the southern side, the dikes are all transposed top to the north and cross-cut by magmatic dikes. So the idea then came out to use these dikes as markers of deformation through time. So if you look at the plane parallel to lineation is like that, and that's perpendicular to lineation. So parallel to lineation, the first dikes are like this, and then dome starts to form. Sorry. And what this is also showing is that it records deformation and magma emplacement during dome formation, during tilting of the foliation. So the first step, these dikes that are then transposed, sheared to the top to the north, and then cross-cut by new dikes that are going to be transposed, and so on. And so that's on the plane parallel to lineation. Perpendicular to lineation, what we see is predominantly shearing towards the west on the west, and shearing towards the east on the east, which is consistent with mingotite up. And you have on the top, where we could find some dikes on the top, either on the north or south, it's usually pure shear on the symmetric axis. So here's the sort of a cartoon model that I built. Is a first generation of dikes rooted in the migmatites that were emplaced before tilting of the foliation, and then after tilting of the foliation, the second generation of dikes, or there are many of them actually, it's not one, two. So what would be the next step if we want to go further? What would you want to do if you had money and an analytical tool to go further? Deepak, what you want to do with your dikes? Want to sample them? Look at the chemical evolution. Mineral, if it reflects some kind of fractional crystallization, or it reflects partial melting at the source, do they reflect differentiation? And also, if you sample, that's what we did, we sampled the most transposed one and the least transposed ones, try to date them. Then you have the timing of the process. And we were lucky, got an age of 60 million years on the most transposed dike, 13 million years on the least transposed one. So it means, and that's beyond, that's significant, this difference is beyond the error bar on each of these ages. And you see the bell curve, these are the ages, number of dates as a function of time. So it's fairly consistent. So it means that this dike transposition occurred within 3 million years. And it gives us the timing of dome formation within 3 million years. I like this one. That's the Möbius, you know, the Möbius torque, or no, doesn't. It's a very peculiar feature. Look at these dikes. Here they look like it's cross-cutting. This one is cross-cutting this one. But if you follow this one, it roots into that granitic pocket. If you follow this one, it's folded and roots in the same granitic pocket. So how do we interpret that? Here you say this one is after this one, but they are in textural continuity here. So they come from the same magma pocket. I think the way we have to take that information is that, well, magma emplacement is not like this. Deformation, which causes transposition of this one, is not like this. Takes time. There's a time for magma crystallization. There's a time duration for deformation. And that's, there we got in trouble. We got in trouble because when we go to the geochronologist guy, they want to have the time as precise as possible with the smallest duration. And us, tectonics person, we say, okay, I want to date something that has a duration. It's incompatible for now. So I think we need to find clues to match these two different motivations. So I'll come back to that in a few slides. This geochronology tectonics difficulty. So the conclusion here, we have a dome with subdomes, a lineation that is dominantly northeast, southwest in the migmatites and in the metamorphic rocks around. But around the subdomes, actually the lineation is radial. So you have two processes here that are controlling the structures. You have probably the regional scale tectonics, which is related to northeast, southwest stretching, falls, and so on. And then a logic which is proper to the migmatite, to the partially molten rocks, which develop their own mechanics with subdomes into a larger dome, probably related to buoyancy, with an imprint of the regional tectonics. It's not saying that it's not happening. Actually, the first of the shape is an ellipse. It's not a circular dome. And here you see that the contact is folded. It's been also sheared. So you have a bit of everything, but in the center, it's mostly, I think, buoyancy-driven subdomes. So let's now look at the zircons. I'll come back to you. Zircons in the migmatites. So this was done by, I lost a reference, but it was our first PhD student with Stéphanie Duchesne, who's the person I worked with in Naxos. And the challenge that we gave her, I'm not sure how I'm doing with the time, but the challenge that we gave her is to date metamorphism, which is still a challenge today. It's not that easy to date metamorphism. We can date crystallization of accessory minerals. How does that relate to metamorphism? It's not a one-to-one relationship. You need to date minerals that you can be sure that they are implied in a metamorphic reaction. But I'm going to do it short. So she found the zircons, and some are very grungy like that. That's terrible looking zircon. You don't want to date that. But in those, she had, and this porous zircon full of inclusion is interpreted as being related to dissolution precipitation. So it's disturbing the uranium-lead systematics. But they have here a nice overgrown zone, oscillatory zone, and that we can get an age out of it, which is 17 million years. Other than that, we have pre-seen zircons with nice zoning. But when you date this, 300 million years, Variscan. But you see that here, this nice zoning is cross-cut by another zone here. And when we did the analysis here, going from the inner part to the outer part, we get 24, 22, 19, 17. And at first, Laure Martin, who was doing that work, said, okay, all this is part of the same, they are slightly discordant. We consider that they are part of the same age. All these dates, his point here is a date obtained by ion beam. Oh, you should have stopped me. Do you know what this is? No. Okay. So we take the rock, we crush it, separate the zircons. Zircons are rich in uranium, and then that will decay in lead, so it's perfect clock. So we separate them, and then we put them into epoxy. And after that, we abrade the zircons to be able to see the interior. It's very important because then you see the texture. And with the ion beam or with a laser, see that's here 15 microns, we are able to do holes of about 20 microns. That's the best we can do at now. No? We cannot go much much smaller because then we lose resolution. And we ablate the zircon, take out all the uranium and lead isotopes, and everything that is there actually, and then separate these isotopes in the mass spectrometer. And you count all the U-235, 238, lead, 206, 207, and 204. And then this allows you, as you know, the decay of uranium into lead, this leads to an age. It's actually, we call it a date. A date is like, it's a data. And then we try to make sense of that, which we call an age. So these are the dates. And as we have two different systems, we have the 235U and 238U that decays both of them in two different leads, then we can have two ages that can match. If they match, they should be on this line. If they're a bit offset of that line, that means that there is some lead loss, and that will change one of these ratios and will offset the data point from the line. So these data are almost concordant. We call them concordant when they are on this line, but not so. So Laure said, okay, I take all these, the dates from 24 to 16, and consider it's one age. And when you do that, when you do the statistics, these are the analytical points. Right? Each of these ellipses translate into 206, 238 age, or date, sorry. So that's each of these spots. And the average of that, when you do the statistics, is this green line, which gives 18.7 plus or minus 2.4. That's the average. And then you can calculate a mean standard weighted deviation. Are you familiar with that? Huh? Which here is 65. The mean standard weighted deviation is a way to test if all these dates correspond to a single age. In other words, all your data points, N, should have a bell curve distribution, and you shouldn't go beyond the 2 sigmas that you consider for your main standard weighted deviation. And if this is the case, that means that the error on each date is smaller than the 2 sigma, then you should have a mean standard deviation, weighted deviation of 1. So here already, something is not matching, 65. When you look at the red lines compared to the green thick line, what do you see? Well, some of the dots are not even covered by the average. So maybe there was something wrong with this date, with this analysis, or maybe it's because it doesn't fit the assumption that we made at the beginning, that all these dates correspond to a single age. Maybe there are different ages there. And this is what we explored afterwards. Say, okay, maybe that trend is significant. It's not part of the same event. And each of these dates corresponds to a crystallization event. And there we lost the geochronologist. He said, okay, no, I'm not following you on that ground. Okay, fair enough. So I made some statistics on groups of dates that could relate to each other and are overlapping. So then we have 16.6, 18.5, 22.1, 24.2. Of course, we need more points to be more reliable. There are not enough points here to do the statistic in a good way. But from that, we can gain that instead of having a single age of crystallization, we probably had several steps of dissolution precipitation, because here, this type of texture reflects dissolution precipitation in cycles of 1 to 2 million years. And you see that here the record is totally different. These are the same dates, and they all overlap. And here, the statistic, I think, is pertinent, because you see it allows, compared to the error margin on each date, it allows to refine the age, and the mean standard weighted deviation is 1.1. That's perfect. So that means that all these might be interpreted as representing one age, same age. 13.3 for this one, 16.1 for this one. And note that the transposition of these dikes is from 16 to 13. So I insisted on the duration, 3 million years, but compared to these dates, these gates go from 24 to 16. So it's before. So you had crystallization of zircon in the core of the lignotite before transposition of the granitic veins. So these are not exactly the same timing. So how now we're going to put that into a single framework? And that's actually where we lost the geochronologist there. He gave me the idea, because these cycles of crystallization of zircon had been identified by the first person that worked on geochronology in this island, and she proposed that the isotherms were moving relative to the zircon, up and down, and related to fluid circulation, to hot fluid circulation that would cause this sequence of event of crystallization of zircon, which is a good hypothesis. But when we checked, we didn't find any signs of hydrothermal alteration, neither in the zircon nor in the mineral paragenesis. And if you play with thermal models, to crystallize and dissolve zircon, it's at least 800 degrees, even maybe 900 degrees that is required. And to play with the 900 degree isotherm, it's not that easy to go up and down in the crust. So it takes time. And we come back to that just later on. It takes 20, 30 million years. So it's not like 1 million years. So the geochronologist said, but it's easy. If it's not the isotherms that are moving relative to the zircon, maybe it's the zircon that moves relative to the isotherms. He told me that like that. I say, wow, brilliant. That's the solution. I said, okay, I don't understand. You just described convection. I said, I'm out of it. He said, I'm not following you on that ground. Convection at the crustal scale. I say, well, if you don't believe it, that's your problem. So let's try now to prove it with physics. Because, I'm sure here there are very different cultural background, religious background, and once we come to religion, then there's no use to discuss. We are doing science. So if your religion says that convection is not possible, then I'm not fighting with you. So I didn't go to religion, I went to physics. So I asked my colleague physician, okay, what would be required for a crust that is partially molten for about 20 kilometers? What would be the condition for having it to convect? Well, if you take a viscosity of 10 to the 18 to the 17 Pascal seconds, which is fairly conservative in terms of what we know about partially molten rocks, then it works. We have a Rayleigh number, which allows to assess if the system is in convection or not. That is over 1,000 for a crust that is partially molten, or layer that is partially molten for 10 to 20 kilometers. And the Rayleigh number is considering the difference in the density, rho, the thickness of the layer that is considered, the heat production, H. Beta is an expansion, thermal expansion. And here is D is the, so D is very important. That's the size of the system. It's D power 5. No? So if you take, and that was the same computation that Holmes did for the mantle convection. He took exactly that number. So you can do it either by heating from the bottom or heating from inside, but it gives the same type of results. Convection is possible. So it went all the way that geochronologists didn't want to publish the data with us. His choice. So that's where we went. Convection with zircon here would crystallize, then go down, be dissolved, come up again, and this several times. That's an elegant way to explain the geochronological record. So how does it go now? Okay, now compared with the dikes. So we have the early dikes. Sorry. First, convection from 24 to 16. So that lasted 8 million years. And then the early dikes start to pick up after the end of the geochronological record in the migmatites at 60 million years. And the latest dikes, 30 million years, record the timing of dome formation. So we propose here that there was a first stage of convection without doming, and then doming. That is the end, the last diapir, if you want, within that partially molten crust. Okay, let's wrap up now, taking all the information we have. So we have a first period of burial associated with the first folds, and then exhumation related to the second folds that is recorded in these rocks. Then thermal relaxation of the thickened crust, built by burial exhumation, increase in temperature. After some thinning, which corresponds to collapse, and the dome formation happens at that time. And then the last exhumation, everything for the last 5 kilometers, all these were exhumed at the same time. So put that into a tectonic scenario, a first stage of burial, and see here I also draw the isotherms. So that's also preparing for the thermal models. And we tried that early on. What is isothermal decompression? And we were not really ready for that. So let's take an example. I take a reservoir of water, hot water, put water in the bath, very hot water, and you put your hand like this. You're not going to, if you do it very fast, you're not going to feel the temperature. But if you put your hand and then wait, then it's going to be hot. Right? So what does it mean? That you have high pressure, low temperature. That means you have burial, but exhumation that is faster than conduction. You get it? So what does it mean if the temperature is increasing? That means that the rocks stay. And then the isotherms go across the rocks by conduction and heat production by radiogenic decay. So the first stage, burial exhumation, and that's preserved at higher structural level. It's preserved at the top structural level. And for the rocks that have not been exhumed closer to the surface, then these ones at depth, they start to see the temperature rise. So that's the second stage. Increase in temperature. And this is concomitant with slab retreat in the area. We know it from the surface magmatism. And then in the last stage, this thickened crust that started to heat up, then was thinning and formed this metamorphic core complex, and that's the time of doming as well. And what's nice about the Aegean domain is that this sequence of events, high pressure, high temperature, and decompression, occurred several times. In the northern part, in the Rhodope, it occurred at 70 million years for the high pressure, and the high temperature about 30 million years after, at between 40 and 30. And 20 million years after, the same sequence of events happens here. High pressure and then high temperature. And today, in Crete, in the southern edge of that, only high pressure rocks have been identified. If we wait another 10 million years, maybe the high temperatures are going to come. You see the logic? And this is all related to construction of the orogenic belt associated with convergence, but as the plate retreats, the crust that has been thickened then thins. Okay, that's, I think, what I wanted to show this morning. What time is it now? 12:36. So we might go through today, if you're not too tired, to how we deal with these observations in terms of models. But we might take a short break maybe, because it's 5 minutes, it's fine? Huh? Because usually we should finish by 1:30, right? 1:30, yeah? Okay, 1:30. Okay, take a break, unless you have questions now, and then try to wrap up these concepts in 45 minutes with models. Okay? Or do you want to keep the models for tomorrow? Depends on how we feel. Take a break.